Assalamu alaikum. Here we are again, third lecture. So welcome. I just continue straight away into the lecture. We were looking at section 17.2, roots and powers of complex numbers. Now we look at sets in the complex plane. And basically, when you think of sets in the complex plane, it's like, go back to real numbers. What did you used to do when you used to look at sets? You would think of lines, circles, things like that. Or should I call them objects? So here in the complex plane, then we will start thinking of, one, we already talked about distance between two complex numbers. Z naught and Z would just be given by that. And actually, it turns out that is this denoted by this, and it actually represents the equation of a circle of radius rho with the center Z naught. I already explained this in the previous lecture, so I hope you follow, okay? And so most things we can say is that now once we have this equation, this represents all those points that are actually on the circle. This x minus x naught squared plus y minus y naught squared square root equals rho. So it's the equation of a circle whose radius is r, centered at x naught, y naught, which is z naught, okay? So now we can think of, here now we're thinking of not the points on the circle, but all the points that are less. From the center, you go out and don't reach rho. So you'll be talking about all those points that satisfy less than rho. So this is the set I'm calling here. S equals all complex numbers such that z minus z naught modulus is less than rho. This turns out to be a disk, and it's actually an open disk, okay? Well, in let me take you back to Math 2108, if you remember. You used to talk about volumes of solids. Specifically, used to have a method that was called disk and shell method. Disk, okay? So you can think of this as a disk because it's just a ball. It's not really a ball, it's a disk like this. Actually, I have a disk here to show you. This is a disk, okay? Forget about this hole. Think of this as the center of my disk. This is my disk. But now the boundary is not, it's open like this. So this is an open disk. So all those points that satisfy that are called in the neighborhood of Z naught. Z naught is an interior point of S. Now our set here. If there exists a neighborhood, we have talked about neighborhood here, which we are denoting by this, that lies entirely in S. What does that mean? That if you go to this set and you pick any point in this set, and then you can find a radius such that every neighborhood of that set is inside the set entirely, then you will say that this point is an interior point. You can think of this as opposed to, if I thought of my point here on the boundary, then any neighborhood I take will have points inside and outside. It's not an interior point. Interior point would mean that the point is here, it's always the neighborhood is within. I hope you can see here. A set S is called an open set if every point of S is an interior point. That means all the points of S are interior points. Then the set S is an open set. The set of complex numbers Z satisfying, now this is another one. Here, if I cover this, we are looking at this disk, okay? And then now if I cover this side, so this we've already said. This is a circle, it's a disk, open disk with radius rho. If I cover this on the side, this is a disk, but now it's the outer part of the disk. This is called an annulus. Actually, this is a nice example of an annulus. You can think of this as the outer one, rho 2, and the inner one as rho 1. This is the annulus. That's what you call an annulus, okay? It's just two rings inside and then the region in between. Then we talk of, we continue. If every neighborhood of Z naught contains at least one point in S, and at least one point not in S, then S is called a boundary point. That's exactly what I was telling you previously here. If I have a point here, in this disk of mine, if I take a neighborhood, it will have points outside and points inside. Such a point is a boundary point of S. If any pair Z1, Z2 in an open set S can be connected by a polygonal line that lies entirely in S, then S is called a connected set. Well, a connected set is simply, like the term says, connected. It's in one piece, okay? You can have, if the set is not connected, then it's sort of disjoint. It's in two or more pieces of a set. Then an open connected set is called a domain. Well, this is just relying on open, and then the connected is just this definition here. A region is a domain in C with all, some, or none of the boundary points. So a region is basically all this. Domain, it has boundary points or no boundary points, all those. So a region containing all its boundary points is said to be closed. So meaning what? That, well, yeah, okay, so the region may be open. In this case, we're thinking of domain. But if it contains all the boundary sets are inside the region, then the region will be closed. Okay? Examples. Let's look at examples. Now here in this section, we only look at two examples. Well, we say two examples, but they have part A, part B, part C, and so forth and so on. Okay? So pay attention. Okay? Now, the first example is, well, actually part 1, part 2. So the unit circle with the center, the origin, is represented by this. You see now, previously here we just said this, okay? Here we looked at, where is this? Here we said this is a circle. If I fix z0 to 0, then I have modulus of z equals, if I fix rho to be 1, then this is exactly what we're talking about here. This is a unit circle. Center is origin, radius is 1. By definition, what is this? Modulus of z. Modulus of z is just x squared plus y squared square root equals 1. It means that it's a circle whose radius is 1, centered at 0, 0. Okay? The second one, a circle with radius 5, center 1 plus 2i has this equation. Modulus of, this is z minus 1 minus 2i equals 5. So, by definition, how would you look at this? You just say it's z minus into brackets 1 plus 2i. 1 plus 2i would be the center of the circle. If you want, you can now use z equals x plus iy, and then you write x plus iy minus 1 minus 2i. You group the real and the imaginary. You will end up with the equation of a circle, which is this really, whose radius is 5. Is that correct? Yes. Example number 2. You have an annulus. Well, now, we've just said annulus. For annulus, the definition we say is just that you have this. Annulus means that you do have the equation of, it's like a circle, but these are two circles. The bigger one and the smaller one. So this is the inner, the outer. So this is basically what you have here, ladies and gentlemen. So, an annulus, the center is the origin. This, now we have the diagram here. This is the real axis, which is x-axis. The imaginary axis, the y-axis. So you will have, now, the bigger radius, here in this case we include 2. So you can say this is 2, and then the smaller radius is 1. So modulus of z is less than or equal to 2. Okay, we include this. And then it is greater than 1. It means that 1 is here, so this is not included. So this is the annulus that we're dealing with. That on this side is open inside, outside is closed. This is the equation of that. Okay, that's the example we have. I hope it makes sense. Next, we have, now here I was not able to do a good job in terms of sketching, but I can tell you. So, this represents modulus of, now this is a circle, but now this is the outer part of the circle. Here, remember when you're dealing with the ball, here we're dealing with the inner part, open disk. Now when you put greater than rho, it means that is the outside part of it. It's more like complement, if you can think of it that way. So, the outer circle, basically modulus of z is greater than 1, means that this is 1. So this one is the outer part. The pink part is the region represented by that. Okay? Makes sense? I hope. Next is you have 2C, which is lower half plane. We call it half plane. Well, simply because of the following. This says the imaginary part of z. Now remember, imaginary part of z is y. So this is like y is less than 0. Now, this is x-axis. Think of it like x-axis. In brackets, y equals 0. So y less than 0 is anything below. So this represents y is less than 0, imaginary part of z. You exclude this line. So the pink part is the region represented. And you can see it divides the whole plane into two pieces. Half and half. So it's called a lower half plane. Okay? Fine. I hope it makes sense. Next is what you call an infinite strip. So here you have -1, or rather the real part of z, which is x. X lies between -1 and 1. Now, this is the real part of this x-axis. And this is the y-axis, the imaginary part of which is the same as x equals 0, and then this x equals 1, x equals minus 1. So this line is x equals minus 1, this line is x equals 1, so x is less than 1, and x is greater than minus 1. So it's this strip, and we don't include the line itself. So this is the infinite strip. For the real part of z lies between minus 1 and 1. That's what it means. I hope it makes sense again. If it doesn't, please do not hesitate to ask and clarify. Okay, I think that's it. I mean, we are done with this section, so I will stop there because I will want to talk about functions in their own right. So is it? Yeah, I think we'll do the next one. So we'll start from here in the next video. So have a nice time or day, whatever time you watch this video.